G'day viewers, this is the long awaited double slit analysis. We'll start with a bit of work on the photon first. So we ask the question, what's a photon? Well, from what we know, it's a massless particle, and we call it a particle because it's a quanta of energy, a self-contained little piece of electromagnetic energy. Now, a photon travels at the speed of light. In whatever medium it's travelling through, it travels at the speed of light. So, for example, through a diamond, it's travelling at about 40% of the velocity of light in free space. In air it travels at roughly 99.97%. It's 299,700 metres a second. That's in air. And I'm sure that varies slightly with the density of the air and the temperature, and I think that'd be the only two variables. We know the energy of a photon is equal to Planck's constant times the frequency in hertz. So the higher the frequency, the higher the energy of the photon. And there's our first problem. The difference in wavelength or difference in frequency is it gives the photon different properties. And I used to be under the belief that an electromagnetic wave was different to a photon, but apparently not. Apparently people want to bundle them into one group. So you have to look at the behavioural, I call it behavioural differences of the photon over the frequency. So the higher the frequency, the more the photon acts like a particle, and the lower the frequency, the more the photon acts like a wave. There is no duality though. The photon is a quanta of energy. It's a packet of energy. And those people that draw them out in little balls travelling away in a straight line from an electron are 1,000 times more correct than the people drawing them as a little wavy line. That wavy line is one of the properties of the photon, but photons don't travel in squiggly lines. They travel in straight lines, and for those people that don't believe that they rotate, well, the magnetic and electric field both rotate. They're locked at 90 degrees to each other. So if the magnetic field is on the x-axis and the electric field is on the y-axis, then the photon's travelling on the z-axis. And it's always handy to use that three-dimensional x, y, z axis as a reference. That's especially the case in electrical problems where you've got magnetic induction causing cross-modulation or intermodulation distortion, or cross-field pickup, capacitive pickup, inductive pickup, anything like that. You do that X, Y, Z three-dimensional, and then you draw your lines out, your transmission lines, and then you can analyse your situation in any small pieces of equipment where your problems are coming from. But a lot of people get confused first with Newton's rings, where he had a concave lens resting on a flat piece of glass, and that left like this is the first clue I got looking at Newton's rings. So he's got a concave lens like that, and he's got another lens like that. Now what happens in there is it's very much like friction, where you get electrostatic bonding. I don't know if any people out there have looked into Kirlian photography, where bits of items have been cut off and then they charge it up with an electric field, and you actually see the residue field of what used to be there. That's a very strange phenomena indeed. But the same thing happens when you put a curved lens on a flat surface. You'll get little bowed out fields. You probably won't believe this, but there is electrostatic fields between any surface, and that's what locks two surfaces together and causes friction. You actually have to break that electrostatic bonding to start moving something. That's why you get your starting friction, and then you get your rolling friction and sliding friction. But at the beginning, there's always that starting friction where you have to break those electrostatic bonds. Now I'd like to mention some pretty strange concepts. It's all electrical, where you've got two field lines of the same field. They don't go parallel. Because they're the same field, they repel each other like this. They don't go straight down like this, they go like this. It's exaggerating it. So straight away you get what we call a stress tensor field across the slit. Now you will notice, if any of you people have read up about the double slit experiment or the single slit experiment, the larger the particle they use, the smaller the slit has to be relative. The ratio has to be lower between the size of the particle and the size of the slit. There's another clue, because you need a higher field density because of the increased size of the particle. But with a photon it's slightly different. A photon doesn't have any mass. But here's where it changes. Because it's going through air, and I'd love to see this experiment done in space. You'd still get the effect, but I don't think it would be as pronounced. Where you've got the, like I said, it's doing 99.96 or 97% of the speed of light in the medium air. It's lost 92,000 meters a second of velocity. Now that little tiny leeway that it's got, that alters the characteristics of the photon somewhat greatly. And the fact that the air is in the gap as well, that is getting affected by the stress field built between the two sides of the slit. Now Newton and Young, back in 1801, they would have had no idea this was going on. These fields hadn't even been thought of. These guys were the pioneers, and you know, I really take my hat off to them for the experimental work that they did. Even with Michael Faraday, that guy discovered the Faraday Rotation, where the polarization of light was actually being rotated through different mediums, and it's used in industry today to check the purity of different crystals. They do a pole test, and you'll see it's, say, like 99.3 or 99.4% rotation through crystals of sugar, for example. It gives you the purity of the sugar. And I know this because I worked in a sugar mill, and they got their what they call pole tests, polarization tests. And if you want to see some really advanced chem labs, go to a sugar mill and see what they do there. They're looking at things right down on a molecular scale, and pretty advanced chemistry. But I don't like the chemicals they muck around with. They muck around with the stuff like lead acetate. Oh, I don't want to go near there. Don't want nothing to do with lead. But anyway, I've got a few notes here. was all about the double slit experiment and about photons, and just, it's like flat earth people versus global earth people, spherical or oblate spheroid earth believers. I believe we're living on a globe. I've been to enough places, enough latitudes and longitudes. I'll tell you what, you notice it up near the equator, it gets dark very quickly. The difference between day and night is very quick, and the sun's directly overhead at certain times of year, anywhere above north of the Tropic of Capricorn, or if you're in the northern hemisphere, anywhere south of the Tropic of Cancer. Depending on the time of the year, the sun could be directly overhead at lunchtime. And there's some interesting things to look up, you know, the position of the sun. You go down to the lower latitudes, right down the bottom of Australia, and you notice, the first thing you notice is the sun's way lower. You notice there's a way big difference between night and day. There's a much longer twilight period. Anyway, I'm digressing. I don't want to talk about flat earth stuff. Where are we? Got lots of notes here. Here we go. Solving photons through a slit or double slit. We're looking at the constants. That's what you've got to analyse, all the different constants. You've got to look at so if we're using a red laser around anywhere 650 to 700 nanometers, you're looking at a frequency wavelength. They're related, frequency and wavelength. Let's go just for the frequency. So that's a constant. The slit width will be a constant. The medium, which is air, that'll be a constant. Assuming you've got it in a fixed setup, your distance from the emitter to the slit and your distance from the slit to the receiver plane. And then you've got to take into account relative room temperature. So this is what I've got here. You can see I've got a couple of little sketches where I've drawn out the field lines on. That's a top view looking down from the top into the slit. And that's how the field lines would look. So there's a couple of possibilities there, and the thing is, why it's forming that pattern is it does have a frequency, and yes, it will be arriving at destructive and constructive positions. So if you've got two photons and they're cancelling each other out, you're going to get a dark spot. If you've got one photon just landing there and no other photons, then you'll get a medium spot. But if you've got two photons landing in phase, then you'll get your brighter spots. So we're looking at different fields around the slit, and it is the slit that causes the problem, and the way we're actually looking at the experiment. If you really want to go down right down to the smallest possible level and analyse the path of the photon through the slit, you'll find there's what they call a tensor of rank 3, and this is manipulating the direction. And one of those is an electrostatic field due to the close proximity of the sides of the slit. And this is why we get a more pronounced deflection the closer we move the slit together. Secondly, on top of that electrostatic field, we have an infrared field coming from the materials. And this is caused because they're not at absolute zero. They're not even super cooled. All the experiments I've seen have been done at room temperature, and at room temperature, on a atomic level, your material is really quite active. The third component of this tensor field is the localized field of the photon. Now, normally a photon would not interact, but the problem is the air has slowed it down. It's not at final velocity. It's not at its maximum velocity, and there's that little bit of leeway. and that photon is just looking to burst out into maximum speed. It's propelled by its own frequency. It's looking to get out of there at light speed, and it's held back by little bits of air. So what's happening is that photon is reacting with that air, with the infrared field, with the electrostatic field, and it is looking for a get out. And it does. It goes through that, and that little air gap, it acts like a lens. So what I'd like to see is an experiment where this is done in space at super cold temperatures with different materials for the slit, and using a standard, well actually I'd like to see two. I'd like to see one done at 650 nanometers, and then a complementary experiment done at 405 nanometers, and that would confirm everything that I've been saying here. So I know you guys have waited 3 weeks, and I gave you 3 weeks for the specific purpose. I didn't want you to just run in and say, oh, that's crap. I wanted to give you guys time to have a look at, do your own research. People like Gary out there, Draft Science, he's obviously done a lot of research into it, and he's looked into it. I've seen a few of his videos. They're pretty good. But what I'm saying here is people aren't considering the other factors that are in the slit there, and I don't think anybody's considered them. So let's have a look at this double slit thing again, or single slit. And unfortunately I'm in the process of moving house, so I can't set up the experiment here myself, but when I shift to my new location, I will have a much bigger area than here, and I will be doing lots of laser based experiments. I'm actually into electrical things, electrical experiments, electrical prototyping, very high speed motors, and I don't really know what gravity is yet. I've got a bit of a lead on it, looking into it. I know gravity is not electrical, but wouldn't it be nice if we could build an electrical machine that could manipulate gravity? And I'm not talking like propeller blades. I want to manipulate the gravitational field with electricity. That's my long-term aim, and I've got a lot of people to help me, and we'll see what we can do. I can usually solve a lot of problems pretty quickly. Sometimes I get stuck. It's like everyone else. You leave it, you go back to it later. But anyway, that's my thought on the double slit experiment and what the cause of the deflection is. It doesn't prove it's a wave at all. It would prove it has wave-like features in that particular experiment, but every other experiment I've seen, a photon acts as a true particle. And an example of that is a photon. Well, if a photon is a wave, how does a photon as a wave travel across 100 billion light years? Or, and they do. We're detecting photons here billions of years old, and they haven't lost any energy, coming all the way from galaxies far, far away from a long, long time ago, like Star Wars, and we're getting these photons, and they haven't lost any energy. They're still the same frequency. They've still got the same initial energy that they left with, and that's only because they are a massless particle. If that was a wave, it'd be the inverse square law, and you'd be lucky to receive it 1 billion kilometres away, let alone 1 billion light years. So that's my take on the view of what a photon is. I'll treat it as a particle of energy. I'll treat it that it has no mass. It does carry momentum. I'll agree with Draft Science Gary there. We do agree on a couple of things here and there, maybe not a lot, but we do agree on a few things. So I agree that a photon does carry force with it, and you can see that with any radiometer or solar, those solar sails in space. They get pushed along by photons. There's one guy who had an experiment with a laser powering a silver disc, and he was shooting it up a pole with this laser that's on YouTube. But that also could be the photons ionising the metal, and he's actually getting ion propulsion. Yeah, but that's debatable. So that's my thoughts on a photon being a particle, and my thoughts on the double slit experiment. If you like, leave us a like. If you disagree, leave us a dislike. And you'll be seeing a lot more from me on YouTube. I'll have a lot better setup. I'll have a bit more professional setup. I'll do some better quality videos, and be able to maybe do some animations and get some pictures up, and be able to explain things a little better. Anyway, thanks for watching. We'll see how we go.